Hi, good morning. Here now I'm recording a lecture for ECE to 10 of the class of this afternoon. 2 p.m. session and 4 p.m. session, same. Now I'm in a situation I cannot stand up or work too long, more than 10 minutes is hard for me. So I cannot go to school to give you lectures, and so I record videos. I will post the video online, and then you can watch them. I can post this in YouTube. Then you just watch the YouTube. You can see to learn from the video. And this situation will last might be a month. So from now on, the rest part of this semester, actually only 3 weeks left. We were working this way. If I have lecture, I record it, post online, post in the YouTube, then you can watch them. And then if we need to talk, we need to discuss, I will schedule the Zoom meeting. All right. So we totally work in the online way. Yeah. You should use for this rate in the period of the past few years. We work like that. And then for, let me see, this week we have 2 lectures, right? So I have 2 videos were uploaded, and you can watch. And next week, we will have no new material. I will use the class as same as the office hour. All right, yeah. And then is another week is a final exam. The final exam, actually, some of you already emailed me and ask for how it works. It will work a similar way as in the quiz. So I work a problem in the blackboard. You can just look at the problem in the blackboard, find the answer, and submit it in blackboard, as same as quiz. But it's not exactly same. We will have more problems, and it will last longer. The quiz, every quiz is 1 hour quiz, right? The final exam will be 2 hours. And it were available in I think it's Tuesday and Wednesday. And Tuesday, Wednesday, that will be the day we are scheduled for the final exam. So I use the same day. You have 2 sessions, 1 session on Tuesday, and another session is on Wednesday. No, I mean the schedule. The university gave you a schedule of final exam. 1 session is scheduled in Tuesday, another session is scheduled on Wednesday. Then I use these 2 days for all of you for the final exam. So you can do it no matter which session you are in. You can do the final exam in these 2 days any time, but not too late. The due time will be the Wednesday's midnight. Like in quiz, I know some of you submit the quiz just midnight is 11:59 minutes, and some of you submit in 12:03. It's late, just a few minutes, but you are late. Yeah. So for the final exam, you can try a little bit early. At least you leave 3 hours to start your exam. Then you have enough time to submit before the midnight. Okay. Another thing different is you only have 1 attempt. So this is final exam. So you only have 1 attempt. So prepare enough before you go to the final exam. All right. Yeah. Make sure you are ready. You are really ready. Then you start, because you only have 1 chance. That maybe you think, oh, that will be hard. I don't know what is the problem. actually you know problem. All the problem, not all, most of the problems will come from the quizzes. We have 6 quizzes. In average, I think I will pick about like 3 problems from each quiz and put them together. That will be 18 problems, right? And select 2 more problems from the material of today and this Wednesday. The totally 20 problems. 20 problems in 2 hours. And most of the problems, they are, you already work on them, right? You already know how to solve those problems because they occurred in the quizzes. So I believe time is enough. 20 problems in 2 hours. Only last 2 problems. Actually, it's similar. Because the material we study today and Wednesday, that is also some old problem. Just to use some new method to solve it. So it won't be so like strange problems. No strange problems. Yeah, our problems you should be feel they are familiar. You have look at them here and there. And of course, all these problems you can find something similar in the Zai book. Yeah. But of course, if you just try to find the similar problem in the Zai book during the exam, that will be hard. You need to already know, then you can find them. If you didn't know, you just try to find them. That will be hard. So before that, you do some prepare. What else for the final exam? You will have 20 problems in 2 hours and only 1 attempt, but you will work in the blackboard the same as you're working in the quizzes. Yeah, I think that will be fine. Yeah, if you have question, you can email me, or next week we have new materials. Then we have Zoom meeting during the class time. Then we can discuss. If you have any question, we can discuss that time. All right. Okay, now let's go to the material we will learn today. Let's go to the Zai book firstly. Okay, Zai book. Here's chapter 12 again. Right? Chapter 12. We already studied chapter 12. We have several chapters. They are related with some basic things about Laplace transform. And now we go to the 2 more sections. We use Laplace transform. We solve the circuit. So we do the circuit analysis as the name of the section 12. Is S-domain circuit analysis. So what is S-domain? After the Laplace transform, we will go to S-domain. Right? We will work in the S-domain. Yeah, the original things is in time domain. And after the Laplace transform, they are in the S-domain. Okay, so here we go to the 11th section firstly. Okay. 12.11 S-domain circuit element models. So here actually this is simple. Just look at here. We have table. Look at the table, then we have everything. Okay, here we list the 3 parts: resistor, inductor, capacitor. And in time domain and S domain, we have different formulas. The first one is resistor. Here's a resistor. We have a current that go across it. Then the voltage will be drop, right? The voltage drop in the 2 sides of the resistor, right? So the positive side should be higher, lower. The negative side should be lower. And the current go from the high voltage side to low voltage side. The voltage drop here is V. V should equal to R times I. R times I. Alright. Yeah, R is a resistance. So for same I, larger resistance will drop more voltage, right? It makes sense. Okay, this is the Ohm's law. Actually, this is Ohm's law. We should learn this very very familiar with this, the Ohm's law. Now we go to the S domain. That means we perform Laplace transform. V should be a function of t. Okay. Now after the Laplace transform, turn to be capital V. This is a function of S. And R is a constant, still constant, nothing changed. And I will be a function of t. And the capital I will be a function of S. So in S domain, we have this one. It looks, seems like almost as same as the time domain. So for resistor, you can think they are same. Just change lowercase letter to be capital letter. Here might be a little bit confused in the circuit analysis, resistance circuit analysis. We use capital V, capital I for constant value of V, constant value of I. So if I is a constant, is a DC current is a keep constant, or V is a keep constant, we use capital V and I. And lowercase v and I there means the value may change according to time. That is earlier notation. Now here, the capital V is not meaning is fixed number. Now the meaning is function of S in S domain. Okay, so here so far you should remember when you have Laplace transform, we have capital V. That means function of S is coming from the lowercase v. And lowercase v is a function of t. Right. So from time domain, we use lowercase v and I. And the S domain, we use capital V and I. Okay, this is for resistor. And the second one, we have inductor. Inductor. We have inductor, we have L, we have VL, we have IL. IL is the current to go across the inductor, and VL will be the voltage. It's also a voltage drop between the positive and negative side. Okay, this voltage drop is a little bit different with the voltage drop in resistor R. In resistor, the voltage drop is really drop. The energy lost. You lost the energy. The energy was used by this device. The R is, you can think it's a kind of things like a swallow the voltage, swallow the energy. And for inductor, it is not used. It is stored. It is stored. When you release the voltage, right here you have some voltage. Then when I go across, you have energy saved in it. And after that, like you stop the power supply, it will release the power. So here is you have a story. You have story. It will save some energy. And when this inductor is full charge, then this one will act as just as a wire. Remember the DC condition. In DC condition, you can just think inductor. It is just a wire, nothing special, just a wire. Wire. Then the I will be some I current go across it, and no voltage drop anymore, because actually it is a full charge, right? It's a DC condition. Okay, for inductor, what is relation? We know now is V equal to L times I prime. Similar with this. This is V equal to Ri. Now we have a prime here. So V equal to L I prime, the derivative of I over T. So we have this one. And we can also write in the reverse way, use integral. So now is R in terms of V, so L equal to 1 over L. You see, move this L to here, is 1 over L. And the V, we do an integral of VL. And now we need plus a initial value. So both two, they works. Okay, then in the S domain, after the Laplace transform, what will happen? Now we have two formulas. We can use either one. We perform Laplace transform on the first one, for example. Then lowercase v will turn to be capital V. This is function on S domain. And L is constant, is still L. So we have L here. And D I over dt to the Laplace transform. Okay, here, let me write a little bit here. So we have v equal to I times L, I prime times L, right? This one. Then we perform Laplace transform. V, it is capital V. L is still L. And I prime, there will be Si minus I0 minus, like this. You can find this in the table of the Laplace transform. We have two tables, right? One is the pairs of functions, the other is the properties. You can find this from the properties table of properties of Laplace transform. Here, I suppose, I suggest you, prepare all the necessary tables, not just in the book. You print them in paper and bring them before you start the quiz, because you find something from printed out, that will be very quick. Then search in the electrical book, right? You use a book. You go to book. You try to find some tables. Maybe you need to pay a lot of time. Yeah, but if you print it out, just a few papers, you can put them nearby your hand. You just take them. You can have the table, right? Okay, but some common use, some part of you always use them. You are familiar with them, so maybe you can remember. You don't need the table, but I just suggest you print the table, before you go to the start your exam. Okay, so V will be written in this way, and then we can separate these two terms. We can write it as L I. I don't know the order in the textbook, and minus L times I of the initial value. This 0 minus means at time 0 you have a kind of like a turn a switch on. You have action. This is at that time, but before action. This minus. If here's a plus, is after the action, right? Okay. Now go back to here. You see? Okay. SLI. Same order as me. And the minus L times IL0 negative. So it looks like these. They give a formula looks like this. You have IL, you have a VL, why this? Why put the negative and a plus? Anyway, this is L times initial value. They just location. Here's a voltage. The voltage may be some negative value. So negative, maybe that means negative is 0. Actually you just use this figure is fine. We don't need this part. You don't need this part. Just you give a figure is fine. Use the figure as this part. Just the inductor with two. You have two wires, right? Two connections. That will be fine. And we can also have the second equation. This one. They are same. You just rewrite it in this equation. In the left one, you write VL in terms of IL. Right. So VL equal to something related with I. So it's VL. Write VL in terms of IL. And this equation write again as IL in terms of VL. So these two actually, as in math, in the point of math view, they are totally same. Just you move IL to the left side. We can see. How can we get these? Now we have this, right? We have this. So now we want here's a V in terms of I. V equal to something of I. Now what is I? I keep this as Li. were equal to V plus this, right? It's V plus Li of 0 initial value. Now I equal to, you divide it, so V plus Li initial value, and here's S and L. And that's it. If you want, you separate as V over SL plus I over L cancel over S. If you want, you know, it's I in terms of V, so you write in this way. It's 1 over SL times V, right? Plus 1 over S times I, 0 negative initial value. Yeah, something like this. Now we can see which formula the textbook right here. Yeah, it's a V. Oh, they use this one. This one. It's just this one. Okay, it's fine. It is just the. It is just this one. Just this one. It's fine. Same thing. Okay, so you have IL equal to this. All right, and similar we have the capacitor. Here's a capacitor. Capacitor. You have a current IC go across, and VC is the voltage difference between positive and negative side. This is also similar with inductor. This voltage, yeah, it's a voltage drop, kind of voltage drop, but this voltage drop, it is not used. It is stored. Some energy stored inside the capacitor. Yeah, when the capacitor is full charge, here's not. Then here will be totally open. Yeah, this is another side of the inductor. In inductor, when it's a full charge, you can see this is just a wire. It is connected by a wire. Right? And here, when it is full charge, you are consider it as a totally open, not connected. Totally open. Right? Totally open. Okay, that is the DC condition. Now the equation is the relation between I and the V and the C will be this: I equal to C dV over dt. And if you write in reverse way, then V will equal to 1 over C times the integral of I and plus the initial value. Okay, then we can do the Laplace transform. Let me see which one directly one. Okay. So this one, Vc equal to, this one is coming from the integral. We have two. Actually, they are same thing. But the first one we can come from either one. You can use either one. So, okay, so this one, the Vc one is coming from the second equation. So capital Vc equal to 1 over C times this. Okay, let me give the process. I copy this one on my paper, then I show you. 1 over C integration. Alright, C dt plus Vc at 0 negative. Okay. Yeah, this one I just copied from the textbook. Now we perform Laplace transform. Vc, now it's capital Vc. Actually, here is a Vc of t. This is a Vs of f. Equal to constant 1 over c. Just keep it. Then the integral of function, there will be 1 over s times that function in s domain. And plus, this is a constant. Constant, I just keep it. But constant times 1. That 1 by Laplace transform, it will be 1 over s. Yeah, this one. This is sometimes people were confused. You know, you were thinking, okay, this is constant. I just keep it constant. But actually, this is constant times 1, and the 1 will go to s domain after Laplace transform. It will be 1 over s. You can find it from the table. Yeah. Okay. Now, can I do some simplify? Yeah, just 1 over c s times I c plus 1 over s times Vc of 0 minus. Okay, so we have these, and we can compare with what we have in the textbook. Yeah, same thing, right? Same thing. Okay, after we have these, we can also have another equation. This first one is VC is written in terms of IC, right? VC equal to something of IC. Now we reverse we write it as IC in terms of VC. We can just coming from the first one. We can see like this. We have this, right? Now let's write in terms of IC into VC. So I move this term to the other side. So I have VC, right? VC I keep it. And this one move to this side, it will be negative 1 over S times VC of 0 minus equal to 1 over CSIS. Okay, then I times CS on both sides, or I say you move this CS to the left, to the other side. Then I have IS equal to this one times CS. So it's CS times VC minus 1 over S VC 0 negative. And I times them term by term. So first term is CS VC, and second term, you see S cancelled, so minus C times VC 0 negative. Alright, so this is a same equation, but I write it as IS equal to something in terms of VC. So IS equal to SC VC minus C times VC 0 negative. Same, right? Same here, same. All right. So for this section, it is just introduced as when we have these three devices. We have these three devices. Each device we have equations of the values. Like the first one is Ohm's law. We have the equation between V and I. You also need the resistance R in the equation, in the formula. And second one, similar. The relation between V and I, you need this L. And third one is also relation between this V and I, you need the coefficient C. Okay, similar, but not exact same. In the resistor, this is algebraic equation, R times I. And the inductor, you need the integral. In the integral derivative, yeah, depending on which one which one is which one, right? You have two equations. You can use either one. But one is enough. Okay? So derivative or integral. Here is also derivative or integral. This is in time domain. And then in the S domain, after the Laplace transform, you can see for resistor it's the same. It's still multiplication of R and I. And here for inductor, and here for capacitor, you can see for both of them we do not have integral anymore. They are also algebraic functions. So VL equal to S times L times IL minus L times IL0 bar, the initial value. So here we only have multiplication and subtract. If we write in this way, we have a division plus and another division, right? So algebraic calculation. Similar for inductor, right? You see both these two equations, they only have some, you times something or divided something or add something or minus something. Algebraic operations. Okay. So here actually we have a idea. We can have the circuit. When you have a circuit, you write equations. You can try to give the equation in S domain. In S domain. Remember, in the previous section, previous 3 lectures, like 2 weeks, we studied the method to use Laplace transform as we give equation, then perform Laplace transform, then we have equation in S domain. So we start from equations in time domain, and by Laplace transform we have equation in S domain. But now we can start from here, because each device we already have the description here in the S domain, right? We have all the equations of these 3 devices. They are just some algebraic equation. We start from these equations, Then we can also write write equations of a circuit, and that in those equations you will not have integral. The integral or derivative will be replaced by like a times SL or divided by like a SC something, right? Times SC. So times or divided by some number times S. They are related with integral or derivative in time domain, but in S domain they are just algebraic. So here, look at here, we have new concept. We call it impedance. Impedance is the name of these three: R, SL, and 1 over SC. Actually, you look at here. V equal to Ri. V equal to Ri in time domain, and in S domain both is V equal to Ri. So this I is that parameter. Is impedance is R for resistor, and for inductor it is V equal to SL times IL. Minus something of initial value, but you can think the case initial value is just 0. Okay, so we suppose before we start the system, start the circuit contains nothing, so initial value is just 0. Then this part is not necessary. We only have V equal to SL times I, or I equal to VL over SL. We just use this SL as the impedance of the inductor is SL, and the C is 1 over SC, similar. See? Okay, so by this way we have these three devices. They have a uniform way to give the relation between V and I. V were equal to a number times I. That number is ZR or ZL or ZC. It may be R, maybe SL, maybe 1 over SC. It's called impedance. So it is how to say, the impedance times I equal to V. We always have these. We all have these. You can write it in this way. Did we have this formula? They didn't put the okay, impedance. It is a V equal to Z times I. Z is R or SL or 1 over SC. Now, this one is for resistor. This is for inductor. And this is for capacitor. We have a uniform way. V equal to Zi. V equal to Zi. Z is as similar as R. Similar. Right? For resistor, it is just R. But for capacitor, is this one. Inductor is this one. Right. Yeah. Okay. Alright. So by this way, if we have a circuit like this one, this is example, we can do S domain analysis. When we have a circuit that looks like this, I can change each part writing this way. L, not L. You should put the SL. Here you need to put SL. Here you need to put 1 over SC. They put this one. Anyway, yeah, you should understand. So when I go across it, you have a V change. The voltage drop in S domain will be this value, no matter which one it is. This value here times I. This value will be here should be SL. This should be 1 over SC. 1 over SC. You can write in this way. Let me copy the picture. We have Okay, now I'm copying the picture in my paper. This is L, this is R1, this is R2, this is C, and this is VS, this is IL, this is VS. Okay. Right, we have this circuit. I is this way. And now, by Laplace transform, yeah, we can write in this way, or S domain. Why is it shake? Sorry. Okay. Okay. So by Laplace transform, we have the circuit in the S domain. So here is still the source, but we S domain there will be Vs. Now here is a lowercase Vs of t. Here is a capital Vs in the S domain. And then here is IL, capital IL. And this L will be SL. And this R, okay, R is still R. R is still R. And this capacitor will be 1 over CS. Okay, things look like this. The circuit world looks like this. And the voltage drop from here to here, it will be IL times SL. The voltage drop here will be this I times this R1. Here will be this I times this R2. And here will be the I from along this path times 1 over CS. 1 over CS. Okay. If I like suppose here is a V0. Suppose this is V0. Then here's like a V1. Then we know Vs minus V0. This is voltage from here to here, will equal to SL times IL. And voltage from to here, the V0 minus V1 will equal to, I don't know what is I. I give I here. Like this is I1, the I2, this is I1. Right. Then this is a I2 times R2. The voltage from here to here is a relation, this one times together. And then the V1 is what? V1 to here, V1 to here. This is ground, the negative side. I said, suppose this is ground. Then this V1 will equal to I times 1 over CS. Alright. But all these, they are in the S domain. In the S domain. Now we can have more equations, like here V0 equal to I1 R1. Yeah, so we have this kind of thing. And when you solve it, because you have S, so the result will be like a V1 equal to some function contain S. V0 will be some function contain S. And let's see what is the question here they ask for. Assume here. Answers may include numbers and or S. Yeah, answer may contain S. Assume initial value IL0 is 1. Oh, suppose here we already have some current, is 1 ampere. And VC, where's VC? Is not printed in the figure, but the C should be the capacitor. So suppose the capacitor already have 2 volt, has 2 volt. So we start at the initial time. The system is not the empty one. It is already run for a while, so it has 2 voltage here. It already stores some energy in this capacitor. Okay, in circuit B, the L box will have impedance ZL equal to O. It's like this. So here will be what? It will be L times S, right? L is what? It's 3, so 3S. Yeah, 3S. Okay, so so the L will be 3S. This is ZL, 3S. And then L box also contain a series voltage. The L box. What do you mean? L also contain a voltage, a series voltage source. What do I mean? It contains the voltage source. Yeah, the statement is a little bit strange. Actually, the voltage change, voltage change. It's a negative L. Oh, not voltage change. This is a initial I0. So what I mean? Okay, so we can think that the meaning, I think, is like this. Initially we have some current go along this way. So that means here we already have some charge inside. We have some charge inside, and that charge is definitely the initial value. So the I has an initial value, right? Yeah, initial value. That initial value, it is here. This one, this is initial value. So we consider all. So this meaning they put the battery here. They think this initial value is coming from the battery. Yeah, I think the reality, the initial meaning is like this. They want to tell us the capacitor already contains some energy, and we think that energy is a kind of battery. It can supply energy, right? And by this way, you can think there's no energy stored in the capacitor, in the inductor. The energy is here. Energy is here. Okay, so I think that is the way. Yeah, I suppose you have that one. That contains the series voltage value is this one. Okay, so it is just negative L times. Yeah, you get this. And third question in the RI box. Okay, so this is just R1. What is R1? R1? Do you have values of R1? No R1. What is R1? R1 is 1? How do we know R1 is 1? The estimation kit is it's here. R1 is 1. I'm sorry. I just look at here. I can't find what is R1. Yeah, in this one, R1 is 1 ohm. R2 is 2 ohm. Okay, so R1 is just 1 ohm. All right, no doubt. And then in box C should be 1 over SC, right? It should be the box C contains ZC should be 1 over CS. 1 over CS. C is 4. C is 4. C is 1. What is C? C is here, also in the figure. C is 4. So 1 over 4S. 1 over 4S. And the next is box C contains a parallel current source. Okay, so parallel current source is this one. If you write I in terms of V, then you have this part. So this part will be here. So ILC inverse over S. It will be CV0. CV0, right? Yeah, CV0. And in the table. Oh, I look at here. You see here? Yeah, C. This is this one. C times VC0 bar. Yeah, this one. I see you have this one. C times VS. C times V at C times VC and 0 negative. Then plug in C is 4 and VC0 bar is 2, so totally 8 ampere. It's the initial value of I. Yeah, that's it. And we can also see this one, what happened here. Let's start S domain circuit element model. We start, we have these, then we got this one. What is the value here? Now this is a inductor. So this side ZL will be S times L. So just 7S. Is it 7S? Yeah, correct. Okay. Well, this book is how to say, is clever than our blackboard. If you put the letters, or like you put a 2/3, you have that bar, the slash bar, 2/3. Then the blackboard will not recognize it. And you can 2/3. You should put the point 6, whatever. How many 6 do you want? Yeah. Okay. But cannot put like a 2/3. And here you can have something like that. Okay. The first one is just 7 times S. The next. Now is a inductor. A different inductor. Okay, got it. 3. Yeah. Next is a. Oh, I have to do it again. Try again. I'm sorry. It still is. It's a CL, right? It's a L, SL, right? So it's L is 3, so 3S. Okay. The next. Oh, every time the number is changing. Yeah. Okay. Now L is this one. What is ZL here? Yeah, it's still same thing, right? 4. Should be same thing. There is a 4S. Right, it's 4 times S. Oh, I also need to put it here. Then the initial value. What is the initial value? I forgot. Do we have initial value here? It's 0. If no initial value, then it should be 0. It should be at 0. This is 4S. And here will be, if no initial, any initial, it didn't claim it's supposed to be 0. Where's the initial? Initial is 3 ampere? Huh? Oh, they put it here. I'm sorry. Yeah, they have initials here. You have initial of I is here. I is here, then I times L. Then you get 12, so it should be 12 volt. Okay, just next. Oh, it should go back. Alright, so this is a 6S. Check, then try again. Oh, I always forget this. This is 6S, and here will be, they have 2 ampere, right? 2 ampere. I have this times L is 6, that should be 12. And next is one. Still this way, but here is parallelly connected. So here is the same. Is I times. I can't type. Okay, it's a 7. 7S. 7S. And here, okay. It's an initial value. I cannot remember the formula. It's this one. It's a capacitor, inductor. This is capacitor. Which one is here? It's inductor with some current. Inductor, this one with current is this one, so I over S, IL over S. This one, A over S, so it's A over S. A over S, right? Over. Oh, it's over here. This is a bar. You see the just over the block. It's a bar over S. So just put I. Let me check. Yeah, you got it. Over this. The next. Yeah, similar thing. So this will be 1 over CS, right? 1 over CS. Okay, now is a 15 milli. 15 milli. Calculate 1 over CS. 1 over CS, and CS is a milli. For this is no, what's the number? It's a 15. 15. So this is a 1000 over 15S. Now we can do some simplify. 3S here is a 200. That will be 66.66666 over S. Yes, something over S, right? So this should be 66.66, whatever. I put the 7. Am I good? Just 6, 7 is enough. Okay. Yeah. All right. Okay, you can do the same thing. You can try to finish the rest. Should be similar. We will go over all these 3 devices with different equations, and they are initial value. Considering initial value is coming from the source, voltage source or capacity source, series connect or parallel connected. All right. Yeah. Okay. What's the time? 52. Oh, I'm sorry. I have 2 more minutes used. Okay, that's all for today. Then see you next time. Will be Wednesday. I will have another video for Wednesday's class. All right. Bye bye.